Today's session is going to address a number of areas within our software, focusing on model setup, components of our hydrology and hydraulics, and modelling and results information. We do note that we do have a follow-on webinar that's going to focus on reviewing your models, and we certainly hope that you can all join us again then for that particular session. And of course, through the course, I'll show a couple of typical models to demonstrate our items. And at the back end of today's session, there'll be some time focused where people can add questions, and we'll address all those before people finish up. So straight into it. So model setup is very much an important part of any stormwater model. And into model setup. So yeah, modelling is very much reliant upon numerical data inside your model, and without this information, fundamentally you won't have any reliable output. Within our software, we highly recommend to our users that template files be an immediate source to create new files, and with each installation of XPSWMM and graphs, we supply a number of template files, and these are located within the template directory under your installation. One of the recommended templates that we do provide to our users is the in Storm and Swim are the Master 2006 metric and US versions. Obviously they're unit variant. And a key component to these particular template files is a big focus for me today is XPTables. I certainly consider them my best friend when I'm undertaking a model, because they help me quickly input and review data. So within the master template files, one of the core bonuses of these files is that they do have all of the tables set up for all of the components in our output files. And data can be copied and pasted within the tables, and also brought into the software from external databases such as Excel or Access databases or any other GIS database format you may have available to yourself. We also note that custom variables can be created in XPTables, where users can define their own equations as required. These equations, I'll go through that process and actually add a couple into an example in a few minutes. XPTables can also link to our quick data view, which is available through an icon on the desktop, and I'll show that in a moment. And that allows you to, when you highlight on any individual element within the software, to see the parameters within that particular table. And as you can see on the bottom of the window shown here, we can review node information, link information, and GIS data. So when you highlight on GIS data, that will show the information associated with linked GIS files, such as shapefiles or mid-views. Model job control specifically relates to the background components that feed into our engine. Without appropriate job control information, the model simply won't run. This is consistent with models across the board. Time control is a critical element, and this is something that, again, I made a point in that first off point. Job control is one of the first points that XP support engineers and support staff review when models are submitted by our support portal via that website. And also note that for our users, if you're not registered on that website, please do so, because it's the immediate support point for our users. Time control within job control between the runoff and hydraulic layers are critical, and there's talk between the two layers within the software. We need to ensure that if you're undertaking temporal pattern modelling, that those time points do hit the same point. 2D job control is separate to the hydraulic job control, and is available to users who have the XP2D modules for XPSWM and XPStorm. One of the core components of a 2D model is to ensure that your time step in this component of the software is no greater than half the 2D grid dimension. So, for example, if you have a 2D model with a 5-metre grid, then we certainly would not expect to see a 2D time step greater than 2.5 seconds. Default land uses are another important component for a 2D model, and they define surface roughness information and loss relationships if required, and this particularly applies to models that have direct rainfall, and that loss relationship will obviously be the infiltration processes, which may be an initial or continuing loss. Double precision is another element of 2D job control, and that's required when direct rainfall models are being assessed. So as you can see on the bottom of this particular slide, this is the 2D job control, describing those core elements we've just noted. So time step, default land use, and double precision solver is in the middle there, these three checkboxes. Another important component that we do make particular reference to is the viscosity formulation equations, and these form part of the shallow water equations by the 2D engine. The current recommended values for the Smagorinsky coefficient is 0.5 and a constant coefficient is 0.05. And we do note that for people who have long-term models, these have changed over the last couple of years, and if you do open up a model, particularly from pre-2011, that those parameters have changed. Under the model output component of the 2D job control, we get to display 2D information. Hopefully most people who are attending this particular webinar may have seen 2D output. We'll get to see values in this particular example at a 60-second time step. However, that time step can be varied, and depending on what your intention of your model is, it may be you're only interested in maximum water elevations or maximum results across any time step, in which case you could increase your map output interval to an hour, effectively 3,600 seconds, or any greater value. Obviously that does limit your ability to review the performance of the model, but that is certainly an option available to our users. A recent component to the software is the time to inundation features. And in this model output option, users are able to define specific triggers, such as maximum curb height depths or peak depths within roadways, or any other desired elevation. That could be a trigger point for your reporting. Under the Levels tab, initial water levels can be applied to the 2D domain, and in this way any level that has been set will be applied across any element that is below that level. And this is independent of the 1D component of the software. The next important element that is a point to review is how 2D cell checks are undertaken. Generally, most users will have the adjust raise or lower options based on the invert or spill crest options, and that relates to the ponding options in the 1D environment, and I'll show you those a bit later on. What I just make mention to there, with depending on the option, particularly the lower to channel bed, one thing that we've noted in support in a few instances is where users have other 2D elements such as elevation shapes, regional galley lines, and that these items are actually overridden where a 1D element in particular is linked to 2D or an interface line is linked to 2D, and that is something that you should certainly be aware of, because otherwise those elements will otherwise be lost. Under the advanced settings in 2D job control, we have a few parameters here, and we do make note that those parameters should be used with some degree of caution. For users who have older models that may be opened up in newer versions, you may see in particular the defaults pre a certain year, pre-2012, 2009 for example, and we would certainly recommend if you are upgrading that model into the more recent versions of the software, that you avoid using those parameters. That's something you should look for when migrating your models. With the new formats that the TUFO engine creates, which is the XMDF format, we have the option to still create DAT files that have been created over the last few years of the software, and that can be undertaken with the map output format and either the pure DAT, which will only produce DAT file results, or the XMDF DAT option, where both sets of results will be available to the user for post-processing. The next element of model setup is configuration parameters. And just before we jump into this element, I'll flick over to a model and just show you where configuration parameters are relative to our job control. So job control is located under the configuration menu. Under job control, we have options for runoff, hydraulics, sanitary for our swim users, and also the 2D model settings. Under the configuration menu is also the configuration parameters option. So we click on configuration parameters. This is where we can start to add parameters. And I'll just type one in as an example, which I'll talk about in a moment, which is min-len equals any given number. And we can add that parameter, and that will form a component of this particular model and override our 1D engine. Some common parameters in the software are cat slope, which is a parameter that converts the slope parameter in our hydrology layer to a percentage instead of meters per meter. ZREF is similar to min-len, where the elevations within a 1D environment can be flooded based on a default water elevation, so it's ZREF. So for example, if you are working in a coastal environment, you would need to apply, for example, a HAT elevation of maybe 1.2 meters, and that would fill any element below 1.2 meters with a water elevation. The next parameter is show continuity. The show continuity option is an option which displays a continuity summary at the end of the model run. That information can also be found via the output files. And that's a quick summary of those 4 parameters inside the software. One of the next elements in model setup is the digital terrain model. A lot of users will use a digital terrain model to support 1D or 2D model. Obviously they're required for a 2D model, but they certainly help users define invert elevations or spill crest elevations in your 1D model. One thing to note though, of course, is that users need to understand the limitations of the data that they're applying to the software. And this particularly occurs at boundaries of the model or at null areas. And we can see in this particular example we have a series of broad triangles. And this occurs in all software, so this is not necessarily just applicable to the XPSWM environment, of course, or XPStorm environment. But that's a standard issue with the triangulation of survey data. We also note that once users do have a terrain model inside the software, that they can dynamically review the Z values in the software via the status bar dynamically. We're going to jump into some hydrology input points. Users can use the catchment tool as a feature within the software to define your catchment areas. These are total catchment areas, and then link to specific nodes to calculate those total areas. This is a handy element for quality assurance inside your model. In this particular example, we can see here we've linked some areas, and we can calculate those areas under Tools, Calculate Node, Catchment Areas. And in this instance, the old area was 0, they were raw nodes, and they've been applied with the data on the right-hand column there. For users who have, or particularly like to use Lawrence's method, we do note that catchment areas can be applied away from the primary first and second catchments, as I've actually shown in a previous slide, to then split that information, potentially using custom variables that I sort of mentioned earlier when we first looked at XPTables. We can do that based on a design fraction impervious value, if that's appropriate, in XPTables. And I'll show this as a demonstration momentarily. But in this particular example, we can see that the total area was applied to catchment 5, and then using a custom variable split, accordingly. I think in this particular instance they might take the front, but we'll fix it up in the next example. And so this is all what things look like in XPTables, but rather than spending time here, I'll just flick over into to the software and show you how to create a custom variable. So XPTables can be viewed in the software either via the XPTables icon on the top row, or it can also be found via the results XPTables menu, or you can also press F2 on your keyboard. So when we're in XPTables, this particular file has been started from our master 2006 metric template. And I'm just on the physical hydrology tab in this particular example. To modify this particular table, we can press the Setup Tables variable icon next to the question mark for help. This particular dialog window shows the parameters that are inside the table. We can see these values, so node name, etc., through. And on the left-hand side, we have all of the node parameters at present available that could be added into this particular table. In this example, I'm going to change this. Instead of inserting a variable type of a node, we hit the drop-down menu. We can add a custom variable or a heading. When you select custom variable, obviously the parameters on the left are no longer available. And I'm going to hit append. In this instance, I'm going to append 2. I'm going to assume in my example model that I have a fraction impervious of 60%. So what I'm going to do, I'm going to rename this particular parameter to 0%, beg your pardon, and the next value to be 100%. So this is very much for Lawrence's method, and for users who are familiar with graphs. To edit and create the custom equation, we can press the Format button on the right-hand side, or we can right-click on the item and go Format. From this particular dialog box, we can then go to the bottom right-hand corner. We have a Formula button. On the Formula dialog window, I'm going to insert 2 lines in this particular example, and the Variables button identifies the parameters that are available from the table itself. So in this instance, I'm going to modify my area value. I'm going to multiply, and rather than multiplied by the value from another parameter, I can actually type in a given value. And in this instance, obviously the impervious component is 40% of my total area. I'm going to select OK there, OK, and I'm going to repeat that process quickly for the impervious area. And this time, of course, it will be times 0.6. You can now see that that equation has been applied across these items. And so I'm going to then go to my active subcatchments drop-down menu and go to subcatchment 5. Just isolate that particular subcatchment where those areas have been linked. From here, I can then select my pervious areas by highlighting those using Control-C or right-clicking and copying. I can then go across to subcatchment 1 and paste that information into the area column here. Again, either by Control-V or right-click and paste. Oops, sorry, that didn't copy. Oh, no, that didn't right. And likewise, I can come back to catchment 5, highlight the balance values, and go to subcatchment 2. And again, you can right-click and paste that information. It's obviously already there, some minor modifications. And that's how we can simply create custom variables inside the software. If we then go to all subcatchments, I can then use this as that example to undertake a quick QA review on my model, where I can review my total area 0.644 for example, and check that 0.258 and 0.36 are applied across my active catchments, which are subcatchments 1 and 2. I'll jump back to the presentation. When developing a model, users, as we've described, should be using XPTables as a key method to review the model prior to solving it. Some other points to check include ensuring you've got consistent hydrology within the software, making sure that your loss model input values are available. Without those, you will either receive a warning or an error when you go to solve the program, and also review that the slope and width parameters are appropriate. We do note that for our Lawrenson method users, the width parameter is not required, although it does need to be a non-zero value, such as 1 for example. As we've just shown with the custom parameter option, Lawrenson method does require our catchments to be split into pervious and impervious components. For rational method users, users need to review or should review the method to determine the time of concentration if you have done that within the software itself and not gone with a direct method, for example. And this just sort of shows an example where, obviously we've done this on purpose, where, for example, under the routing method, we have some inconsistent hydrology, and that would be generally considered inappropriate. We do make note that XPSWM and XPSTORM are stormwater infrastructure models. As a result, small diameters should be avoided. The default value within the software is 0.05 millimetre. We also note that the minimum length by default is 10 metres, but using that configuration min-len, we can override that value, and that would be required, for example, for short pipe lengths across roads or road crossing culverts, for example. The 10 metre length, though, is certainly something that I would look for when reviewing a model, because, and as we've done here with, as an example, we've gone into the link table in XPTables, and we've sorted by length to identify some 10s. When I then go across this table, I can see that clearly these two links here haven't been reviewed, or data has not been input properly from an external database if that's where the data was coming from. So that's certainly something to quickly review. XPTables does help us do that with the sort functions. Another option within the software is a simple review point prior to solving your model is our dynamic longitudinal sections option. Dynamic longitudinal sections can graphically show that the network is at least graded correctly. We wouldn't want to see any irregularities unless they were a functional part of your model. I do note that in this particular view we do have links also to the XPTables with link parameters at the top and the node values at the bottom, and that these items can be turned off using the two icons just to the left of the base scenario drop-down box. That's particularly handy for people who have small screens on laptops. Another item that is very important for within the hydraulics layer is our node ponding options on our 1D nodes. Node ponding is in the middle of the node input window, and there are 5 options. The 3 very important ones are the top 3, and sometimes generate some degree of confusion, and I'll just quickly describe those. The none option allows the model to fundamentally lose water when the HGL exceeds the value applied at the spill crest. And when this is done, that's fundamentally a warning to the user and can be flagged in the output file. We call that flooding in the software. In a stormwater environment, if you have flooding on a 1D node, that's typically an error in your model that would certainly need further review. The allowed option provides the option to link storage information via the storage dialog box below, and that storage information can be applied actually from the spill crest elevation, and so therefore you actually have a storage point above the ground on that particular node. and therefore water would not be lost from the model. The sealed option represents fundamentally a bulk down manhole lid or a sealed lid of some description, and in that particular instance the spill crest elevation is fundamentally raised by the software in line with the HDL, again without losing water from the model. The bottom two options are 2D ponding options, and hopefully are reasonably straightforward, and that's where we would link the spill crest to the 2D, and that would be linking a gully lid or a graded inlet to the 2D, and the inverted 2D is where we'd have a road crossing culvert or a headwall linking to the 2D. Well, we can check the ponding option again under using our XPTables via the junction data table if again you are interested in using the metric table, metric template of each part. For results, so we'll just briefly go through results. Again, we do have a follow-on webinar, as I mentioned earlier, in February, and again, very keen to have as many of you get involved with that webinar in February. But reviewing your model is very important, making sure the results that you have been reviewed prior to preparing any reports or providing input to any authorities or any other reviewer. One of the key components of the numerical model is to ensure that continuity in other areas are addressed if presented. We can get into our error details and output files via the Analyze menu, and also via the Show Output Logs. We haven't got that drop out in this particular slide. We'll show you that in the model shortly. But 2D model uses the show feed partnership across the 2D simulation summary, something I'll show in a moment. Within 1D, again, dynamic longitudinal sections are a useful point in the software to generate a graphical presentation of your data. And in this particular instance, this shows that the magenta line is the maximum HDL. There is a blue line that in this particular instance is mirroring that maximum HDL at this particular time step that I'm sitting at. And this particular icon or element here, that wavy blue line, is identifying flooding from this particular model. So this particular model is actually failing and does require some further review. And what I'll do, I'll just jump over into a model and show that. I'll just turn off my background image to make this a bit clearer. I'll also turn off my catchments. So from this particular upstream node, I can right-click on that node, select downstream objects, which ignores side tributaries, and the dynamic long section icon is 3 to the left of the solve icon. And this presents that same longitudinal section from the slideshow. I can hit play on this particular set and watch that HDL go up and come down at the end of this particular model run. But clearly we need to resolve this flooding at this element, and also at the upstream element. It's a bit hard to see. Again, if users do have small screens, just clicking these two icons at the top maximises that view. Of course, the handy part of having the XPTables set up is that we can then review core information, and one important one on a link is the spreadsheet info table, where I can start to see elements such as maximum velocity, where on link 5, for example, we've got a maximum velocity of 5.4 meters per second. But as you can see, it's not a full pipe, so it's a partial velocity, and should be acceptable. For our 2D users, that 2D simulation summary, as shown before under the Analyze menu, it certainly should be an initial reference point to review the performance of your 2D model. The 2D simulation dialog, like so, and does have a few options under the drop-down menu here, and they include cumulative mass errors. And from a 2D model perspective, ideally you would want to see a cumulative mass error less than 1%, and I'll show that by jumping out into a 2D model. And this particular model, like the other model that I've used, are both available in our Getting Started manual files, and they're provided with each installation of the software. So under the Analyze 2D Simulation Summary option, I get the same window. We can drop down and through the list and confirm a few parameters, for example, that the model runs for 5 hours. It did get to 100% completion. That we do have some 2D negative depth warnings, and they need to be reviewed, and some checks prior to the simulation. They typically are associated with 1D elements that are modifying the 2D terrain. This particular model has a 5 metre cell size, and you can run it at 2-second time step. Via the drop-down menu, we get to see cumulative mass error and also details on flow in and flow out. Again, we'll spend a bit more time on this in the subsequent webinar in February. But again, ideally we want to get to less than 1% cumulative error in the software. But this initial component may be something that will require to review in this particular model. In Plan, 2D results can be reviewed in the network view. And in this particular example, I've just shown some restricted velocity plots. And that can be handy for reporting purposes. You can get into this dialog box by right-clicking on the layer and going into the display properties. And that can help you identify key issues such as high velocity for scour design, or in the water depth layers, points of loss of tractability and other parameters. Time series outputs are another important tool to users inside our graphical interface to extract data from the 2D, which is otherwise generally defined at a cell level. So time series outputs accumulate results depending on which parameter is applied, and they include flow lines or head velocity points. In this particular example, I've shown a plot of the head velocity points, these yellow points inside the software, and we can see we're getting a change in water elevation moving through as the water moves down the terrain in this particular model. For models that do require some more detailed review, users can produce check files, and they're under the 2D job control in that first general pane. The check files can detail boundary condition information, summary information on the 2D grid itself, and also 1D modifications to the terrain. We do strongly recommend that our users do review the help file, which does summarise more information or detailed information on the check files for both the 1D and 2D elements. That brings us to the end of today's general webinar. We do appreciate your time sitting in and listening to today's session. If you do have any follow-on queries after this session, by all means contact XP Solutions at your nearest point, which is likely the Australia Pacific region. And you can contact us via either sales@xpsolutions.com or the support@xpsolutions.com email addresses. And again, I thank you for your time and look forward to any queries if you have any. Thanks very much.